Hello everyone, I'm Xiao. This is the third tutorial of ChemPlasKin. I will show you how to model nanosecond spark discharge in air. This example corresponds to section 3.3 in the paper. You can check reference 11 and 56 for more details. Similar to previous example of nitrogen, we will use external profile of electric field and electron density for this case. You can check the reference 56, ultrafast heating and oxygen dissociation in atmospheric pressure air by NRP discharges. This is one of the most important paper for NRP discharges. We will use the external profiles of electric field shown here. Let's check the mechanism file first. So under PAC kinetics directory, you will see air plasma and GI30 plasma mechanism file. The air plasma mechanism is based on the second GI mechanism file. Let's have a look. So it basically just remove carbon species and reactions, but keeping the same third body colliders. So here you will see some third body colliders. Still, you can choose to use original GI13 plasma mechanism, which is based on Chen's paper, shown here. It's based on GI 3.1 mechanism and methane air plasma combustion mechanism developed by Chen. It's a very good mechanism. Here you have the combustion part. It's based on GI, but we moved all the carbon species-related reactions and air plasma. For some reactions, you may see something like this. For example, this reaction. The heat release rate calculated by enthalpy difference, the conventional enthalpy difference, will get 4.985 electrovolt. This is heat release calculated by delta H. But experimental result can show it the actual heat releasing is 3.5 electrovolt. So this means the remaining energy should be stored in the vibrational states. Therefore, we add a minus 1.485 here. And this energy will go to the vibrational state of nitrogen. Be careful of this energy transfer entry parameters. To run this case, you can simply make dir, that make a directory of build. So here we are under the test case. Let's go to the build. It's empty here. And do CMake. We compile the code. Compiled successfully. Now we can simply run ChemPlasKin without specifying any case directory. We don't need this case directory, okay? Because all parameters are hard-coded. There's no need for text files for user input parameters. We will check the source code later. Okay, it's running. Good. If you check the log output, you find something like this. I will explain to you later. These are some diagnostic output. Now let's just try to plot the result. Go back. The output is this one, output air CSV. Sorry, Python plot. Here you see temperature evolution, this one going here. So this is same as what we plotted here. And atomic oxygen evolution, this one. We also plotted the A3 and C3 states of nitrogen as excited states. Good. Let's move the source code. Again, I'm using C-line. This is very good IDE for C++ programming. Unlike previous test case of nitrogen plasma kinetics, here we use the original plasma reactor header file. We didn't change anything, but we are using a different master code. Now it's called testair.cpp. I will not go to all the details of the source code since I have explained many of the code in previous tutorial. You should check that. So before running everything, we prepare some useful functions, get member density. I've talked about it. Here we have a function to read the CSV data. So this is to read the input files of electric field and member density. We also have in interpolate function. I use a second order quadratic interpolation to find the electric field and the electron density for any given time. Okay, you don't need to go to details of them. Now we go to the main function. You see here, main function doesn't take any input, so you don't need to specify the case directory. If you want to modify anything, you have to change. For example, you want to change delta t and time, you have to change its numbers and compile ChemPlasKin again. So here with delta t set as 0.1 nanoseconds and time is 100 nanoseconds. We include the thermal effect, of course. This is print reaction rates. I think I have talked about it in previous tutorial. Now we put it false because we don't want to print all the reactions. There are hundreds of reactions. It's too much to print out in the terminal. So this is VP and NE is just to read the experiment data and hold it in this vector pairs. This is an example usage of interpolation function serving as a test of reading the external profiles. Again, we need to specify the Boltzmann species to be configured by CPP bolos. Be careful, there could be possible difference of species name in LexCAD and your mechanism input. They may not all necessarily same, especially for the capital. You see this function, find species index. So ChemPlasKin can figure out these four names for electrons. But always keep in mind, try to make the name consistent. We also have some other species to be configured by the Boltzmann solver, but they are 0 at the beginning. In the future, if you want to simulate meson, you can put a number here, or argon as a dilution. Now we read the cross-section data. Again, make sure the path is valid. We set up the grid and initialize the Boltzmann solver and test the running. Okay, now we can set up the gas phase and the reactor. We reading the mechanism file. We can use GI, we can also use air plasma as well. Okay, let's keep the original one. We set up density. We need some seeding electrons, but again, since electrons are read as an external profile, this number will be overwritten. We set up the mole fraction and the temperature pressure state. It's very similar to the plasma nitrogen plasma case in the previous tutorial. Here, again, the non-thermal effect should be null, so it will include the thermal effect. And the constant pressure should turn it to false because we are using constant volume in this test case. We set up the integrator, initialize it. These are just to assess the kinetic information. The same to the previous example. Again, same. Now we are running we can go to the main loop. Here we only have one pass, so the simulation would be stopped at end time. The main time loop is relatively easy. We relax delta t after 25 nanoseconds, but in general, you can consider it's a fixed delta t. Or print out the runtime and dt. Then we try to update the electric field and the number density. Then we set up the electric field and check for the Boltzmann mixture. Update the EEDF. Now we impose the number density and reinitialize the integrator. Next, we advance the time step. Here, you can check the internal integration time steps from the CVOD solver. Here, we write down the output, store the data in the CSV file. And we check the plasma power and energy. So these two functions can be useful. The first one is print top rate of progress, which is here, you see here. It's print top 5 reactions, the most reactive steps. They look same, but because they are kind of duplicated reactions, but they represent different things. For example, reaction 326. You can go back to the mechanism file and check which exactly the reactions are. And also, we have print top species production rates. They are ranked by their absolute value. So the first one is nitrogen. If you go to the end of simulation, the last step, let's see here. Here is time at 82 nanoseconds. You can see it more clearly, which the top reactions ranked by their reaction rates, and also which species being produced most or consumed most. So it can be useful for diagnostics. Again, we have a print reaction rates. If this flag is true, you print all the reactions, not just this top 5, which will make the log output very, very long. So now we turn it off. Here it is. Let's go to the plasma reactor. This is the original one under SRC file, source file. This is not a customized one. You will see something like this. It will register electron index and this species. So here comes a tricky part. If you are using the original plasma reactor, and you have to make sure your mechanism contains this species. Otherwise, you will get error when it reaches these steps, because you cannot find this species. This species is necessary to calculate the vibrational relaxational time scale for vibrational state of nitrogen. In the evaluation function, which get the time derivative of this solution vector. Here you will see it calculates the vibrational states of this species: nitrogen, oxygen, NO, and NH3. But in this plasma reactor, we only consider nitrogen as the major species to store the vibrational energy. So this tau VTO2 will be useless. It will not be used at all. But I provided here, you can, maybe it will be useful for you. So this is the DDT. This one corresponds to the functions in the paper here. Or you can choose the Fleety mechanism. So these are some useful function as we have discussed. Print the top rates of progress and print the top fast gas heating. You can explore them. Let's have a look at the set plasma energy transfer function. So this function register the energy transfer entries. You have to check for the vibrational states of nitrogen, for O2, for NO, for NH3. For your customized needs, you may consider more species based on your specific needs. You can do the similar thing like here. Just copy the code, change this name, then you'll be able to register this vibrational states. But in that case, for example, if you need to consider vibrational states of O2, you have to modify a little bit here. Let's see. Okay, here. So number of equations should be updated, since you need to consider not just vibration state of nitrogen, you have to consider oxygen. So you have to put one more parameter here. So you have to add like star E vib and O2 dot. Okay, you need to add one more variable in the OD system. Again, if you add that one, E vib O2, you have to update here, get states. So get states, E evaluation function, get states, update states, and number of equation. These are correlated. They have to be matched with each other in terms of total number of variables to be solved in the OD system. Again, you see this vibrational states of other species, O2, NO, is not actually solved in this plasma reactor, but you can add them in the future if you need them. That's all for today's tutorial. I hope you enjoyed the video. If you have any question, go to the GitHub or to the Google group to leave a question or comment there. Thank you. See you next time.